to is around somewhere here 15 degrees or so, we start to go down. Right? Look at this. It's very smooth. You don't stall. And if you have a nice shape like this, you can just fit it. Right? So you fit it with this formula that people use all the time because it's very simple and it captures the effect of a stabilized leading edge vortex. The steady effects of a stabilized leading edge vortex. Okay? And of course, it has a formula for drag, but I don't care about drag now. Yes, Dave?
So do helicopters, their rotor splays also have this CL, the same CL?
At high angles of attack, yes. At high angles of attack, yes. The issue is, I'm going to talk about this. This is not complete. So he did this experiment in particular conditions. He got this lift coefficient, and that's it. But because there is no alternative formula, people use it ubiquitously, use it all the way in analysis of flapping flight. So let's see. So steady lift due to stabilized leading edge vortex, we just introduced Dickinson formula. Later on, a few years later, when they said, by the way, you don't have all this kind of complication, it's simply sine 2 will work, and that's it. But it's with an unknown coefficient, and you just fit it. They did this work in the JFM. They fit the A value for 3 insects experimentally, but again, there was no way of getting an analytical formula for A. And I'm just reminding you, this is Polhamos. If you apply Polhamos, it doesn't work that nice. You have to modify it a little bit. Polhamos said that these coefficients, they are strong functions of the aspect ratio. So because of that, we expect that this A is also a strong function of the aspect ratio, right? So we said the following. Well, if this formula is valid for all the angle of attack region from 0 to 90 degrees, like Dickinson and Wang showed, then it means that it's also valid in the small angle of attack region. In the small angle of attack region, the sine 2 alpha goes to 2 alpha. So you have here A times 2 alpha, and this must equal to the linear equation, CL alpha times alpha, which means that this A is half the lift curve slope. So this is what we did, this little contribution that we did. We said, okay, this is actually half the lift curve slope. So, and we can use, from the linear theory, so we can use whatever correction you like, maybe the most accurate one that I like, the extended lifting line theory, to correct for your CL alpha. And if you do that and compare, we get excellent results. So this is for 2 insects. This is the potential flow theory, sine alpha kind of thing. Goes all the way, sine 90 is 1. And this is the sine 2. This is Polhamos after some modification. Polhamos without modification, it gives much higher lift. These are the benchmark results and our results. So it seems that this nice formula works. So at any rate, we know now the steady lift due to a stabilized leading edge vortex, but this is not sufficient. We will know why in a minute. But any questions so far? We know the steady lift coefficient due to stabilized leading edge vortex. Any question about that so far? Okay. Actually, the leading edge vortex was not the only mechanism, the only unconventional mechanism insects use. So it's the main one. Dickinson, in this seminal work, he identified 3. The leading edge vortex is the first. Second, there is this rotational lift due to rotation. In hovering, you have horizontal stroke plane, and when you go all the way, you have to reverse, you have to rotate, pitching, to come back, to adjust the angle. I cannot go and just come back with the same angle of attack. You get 0 net lift, okay? So you do rotation near each half stroke. And the same for forward flight also. You have to, actually forward flight, you rely on rotation much harder. It's not only near half strokes, near the end of half strokes. You continuously, because for forward flight, birds doing like this, do vertical stroke plane. Insects, they do horizontal stroke plane. So in either way, you need pitching motion between each half stroke. And you guys know that whenever we have a pitching angular velocity omega, we get an extra lift. Anybody remembers why? We already discussed this in class. Why when we have, so if this, assume that this is horizontal now, if this guy is at 0 angle of attack, instantaneously you get 0 lift. But if at this particular instant you have an angular velocity, so at a particular instant you are at 0 angle of attack but have angular velocity. So in the very next second you will have non-zero angle of attack. Okay? At this instant, the geometric angle of attack is 0, but because you have angular velocity, you get extra lift. Why? Because what matters is the angle of attack at the 3/4 chord. So maybe the angle of attack of the whole chord now is 0, but if you calculate it at the 3/4 chord, because of the angular velocity, you will get a different value, right? Unless you're doing the hinges at the 3/4 chord. Yes, at that time it doesn't matter. So you get an extra circulation gamma, okay? An extra circulation here. But they call it rotational circulation, but actually this is due to what we know in this course. It is due to basic theory. The last thing is what Dickinson called it wake capture. So when you have an airplane flying, so the wing flies, it leaves wake behind, but that's okay. The thing over there for flapping, you leave wake behind, but then you rotate and come back and meet your own wake. So this is what he called wake capture. You can see this video simulation of our code, similar code, extended version of it, the UVLM code. This green little thing is the flap plate, and the circle is just its radius gives you an idea about the circulation around the airfoil, so it gives you an idea about the generated lift. And you can see that how the vortices shed behind, but the flap plate comes back and encounters the lingering wake again from the previous half stroke. So this is what we call wake capture. So maybe insects, when it comes back in a way that when it encounters this lingering wake, it maximizes the effect and gets extra lift. So it's something new that we don't encounter here. One thing to notice, you see that the vortices go down, so there is a net jet kind of thing, net momentum here, so you will have lift, right? Net momentum for the fluid down, so you have lift upward. So these are the three unconventional lift mechanisms. This latter one is very hard to determine and analyze, and the other two, we know steady relations for them. So let's go here. This is the interesting part. So this is a taxonomy of our flight regimes in general, whether it's flapping flight or not actually. If you have a low reduced frequency, less than 0.1, we learned that quasi-steady aerodynamics may be applicable. So no matter how complicated your flow field is, how non-linear it is, go and do an experiment like Dickinson, get an expression for the CL as a functional angle of attack, algebraic expression, you're done, right? No matter how complicated it is, it doesn't matter. It's a single experiment in your wind tunnel or a single run in your flow solver, and that's it. Okay? So if flapping operates, if we do 4 or 5, for example, burned with low reduced frequency, and even if I have a nonlinear leading edge vortex, I know the steady CL alpha curve. I'm okay, right? Let's go more here. Okay, if you do it fast. So K, the unsteadiness, you reduce the frequency, is larger than 0.1, so you cannot neglect the unsteadiness now. But your flow is still attached. And the criterion here you determine it based on your application, whether it's 15 degrees, 20 degrees, 25, 10. Okay, this is the condition for attached. So what's this branch? This is unsteady attached flow. This is our course, right? So we have in the 2-dimension, we have Tidursum, Wagner, Schwarzensonden, we have Peters, we name it. We have the unsteady vortex lattice, either 3-dimensional or 2-dimensional. Even for the 3-dimensional, which we did not learn in this class, we have some theories. We have analytical results. That's great, right? The issue when it comes here, so it's highly unsteady flow, and it's nonlinear. So in this particular example, we have a leading edge vortex contribution that we cannot neglect here, right? We know the steady contribution of it, but we don't know its unsteady version. because you cannot know its unsteady version. You cannot know the unsteady version of any lift mechanism. Why? Because here you can do it with a single experiment. Over there, unsteady, it depends on the kinematics, it depends on your motion. Okay, if you do it sinusoidal, you will get some lift behavior. If you do it sharp, you will get another lift behavior. You will not be able to tell. It needs a very clever way of doing it. This is a science by itself. This is the system identification. This is reduced order modeling of fluid mechanics. It's a huge discipline by itself.